Hello and welcome to Math Zone African Motives. Today, we're diving into a powerful integration technique. We'll be exploring Unit 4.7, integration using partial fractions. Our goal in this video is to learn how to integrate complex rational functions by first breaking them down into simpler components. By the end of this tutorial, you will be able to perform this decomposition and use it to solve various integration problems. So, how does this work? Imagine you have two or more simple fractions. When you add or subtract them, you get a single, more complex fraction. For example, if we add 2 over x minus 2 and 3 over x minus 3, we find a common denominator, combine the numerators, and simplify. We arrive at the complex fraction, 5x minus 12 over x squared minus 5x plus 6. The whole idea of partial fractions is to reverse this process. We start with the complex fraction and split it back into its original simpler parts. These simpler parts are what we call partial fractions. In other words, partial fractions are the result of decomposing a complex fraction into two or more simpler fractions. Our task will be to start from this complex fraction and work backward to find the simpler ones. To successfully split a fraction, it's crucial that it's a proper fraction. Let's define what that means. A proper fraction is one where the degree of the polynomial in the numerator is strictly less than the degree of the polynomial in the denominator. For example, in our fraction 5x to 12, x to 2, 5x plus 6, the numerator 5 to 12 has a degree of 1, and the denominator x odd 2. 5x plus 6 has a degree of 2. Since 1 is less than 2, this is a proper fraction. On the other hand, an improper fraction is where the degree of the numerator is equal to or higher than that of the denominator. If you encounter an improper fraction, the first step is to use polynomial long division to change it into a proper fraction, which will result in a polynomial plus a proper fraction. In this course, we will focus on two main types of fractions that can be integrated using partial fractions. First, we have fractions where the denominator has two distinct or different linear factors. This means factors of the form x plus b and cx plus d that are not the same. Second, we'll cover fractions where the denominator has repeated linear factors. This means a factor like x plus b is raised to a power such as 2 or 3. These two types cover most of the problems you'll encounter. However, it's worth noting that in a higher level course, you might learn about a third type involving irreducible quadratic factors. For now, let's focus on our two main types and their corresponding partial fraction forms. Understanding the correct form for the partial fraction decomposition is the most critical step. Let's formalize the rules for finding partial fractions. For a fraction f of x over the product of two distinct linear factors, the partial fraction decomposition is a over the first factor plus b over the second factor. This is the simplest and most common case we'll handle. Notice the numerators are just constants, a and b. This is always the case when the denominator is a linear factor. Now let's look at the case of repeated linear factors. If the denominator is a factor raised to the power of 2, like x plus b squared, the decomposition is a over the first power of the factor plus b over the squared factor. It's crucial to include a term for each power from 1 up to n. Similarly, if the denominator is a factor to the power of 3, the decomposition has three terms: a over the first power, b over the second power, and c over the third power. Again, we account for every power from 1 to 3. It might look complex, but we'll follow a clear 6-step process to apply this technique. Let's outline these steps before we work through our first example. Step 1. Factorize the denominator. If you have repeated factors, make sure to write them in their exponential form, like x minus 2 squared, not x minus 2 times x minus 2. Step 2. Split the fraction, not the integral, into its partial fraction form using the formulae we just discussed. This means setting it equal to a, b, and c over the factors. Step 3. Multiply every term in the equation you just wrote by the original denominator on the left-hand side. This will cancel out all the denominators and give you a simple polynomial equation. Step 4. This is where you find the values of your constants a, b, and c. You have two main methods for this. Method 1 is substitution. You choose values of x that make the factor 0, which simplifies the equation greatly. Method 2 is equating coefficients. You expand the right side, collect terms by power of x, and compare them to the left side. We'll see both in action. Step 5. Once you have your constants, substitute their values back into your partial fraction form from Step 2. Now you have a sum of simple fractions that are ready to be integrated. And finally, Step 6. Integrate each of the simple fractions separately. This is the easiest part, as these fractions often integrate into natural logarithms. Now that we have our roadmap, let's put it into practice with our first example. Our first problem is to determine the integral of the fraction 5x minus 12 over x squared minus 5x plus 6 with respect to x. Following our process, we first ignore the integral sign and focus only on the fraction itself. This fraction is already a proper fraction, as we noted before, because the degree of the numerator, 1, is less than the degree of the denominator, 2. Step 1 is to factorize the denominator. We look for two numbers that multiply to positive 6 and add up to negative 5. Those numbers are negative 2 and negative 3. So the denominator becomes x minus 2 times x minus 3. Step 2 is to separate the fraction into its partial fraction form. Since we have two distinct linear factors in the denominator, the correct form is a over x minus 2 plus b over x minus 3. Step 3 is to multiply both sides of this equation by the original denominator, x minus 2, x minus 3. On the left, everything cancels, leaving us with 5x minus 12. On the right, the denominators cancel out with their respective factors, leaving us with a times x minus 3 plus b times x minus 2. Step 4 is to solve for a and b. For this type, substitution is the quickest method. We can substitute values of x that make the terms in the parentheses 0. First, let's substitute x equals 2. This will make the b term 0. We get 5 times 2 minus 12 equals a times 2 minus 3 plus b times 2 minus 2. This simplifies to negative 2 equals a times negative 1, so a is 2. Next, let's substitute x equals 3. This will make the a term 0. We get 5 times 3 minus 12 equals a times 3 minus 3 plus b times 3 minus 2. This simplifies to 3 equals b times 1, so b is 3. Step 5. Now we substitute the values a equals 2 and b equals 3 back into our partial fraction form. The original fraction is now written as the sum of two much simpler fractions, 2 over x minus 2 plus 3 over x minus 3. Step 6. We are ready to integrate. We can replace the original complex integral with the integral of this sum of simple fractions. We can integrate each term separately. The integral of a constant over a linear factor x plus b is the constant over the coefficient of x times the natural logarithm of the absolute value of the denominator. So we get 2 times the natural log of x minus 2 plus 3 times the natural log of x minus 3. Don't forget the constant of integration, plus c. So the final answer is 2 natural log of x minus 2 plus 3 natural log of x minus 3 plus c. Let's verify this with the memo, and it matches perfectly. Verified using memo. There's an alternative way to find the constants a and b that is useful, especially for more complicated problems. Let's revisit our polynomial equation from before. This equation is true for all values of x. This means the polynomial on the left must be identical to the polynomial on the right. If two polynomials are identical, their coefficients for each power of x must be the same. First, we expand the right-hand side. This gives us x minus 3a plus bx minus 2b. We then collect terms that have x and terms that are constants. Now we equate the coefficients. On the left, the coefficient of x is 5. On the right, it's a plus b. So we get our first equation, a plus b equals 5. Next, we equate the constant terms. On the left, we have negative 12. On the right, we have negative 3a plus 2b. We can write this as 3a plus 2b equals 12. This gives us a system of two linear equations. We can solve this system using the substitution method. From the first equation, we can express b as 5 minus a. Now we substitute this into the second equation. 3a plus 2 times 5 minus a equals 12. Expanding and simplifying gives us 3a plus 10 minus 2a equals 12, which simplifies to a equals 2. With a equals 2, we can find b. b is 5 minus a, so b equals 5 minus 2, which is 3. We get the exact same values for a and b. While this method involves more algebra, it is more versatile and guaranteed to work in all cases. It's especially useful when the substitution method doesn't provide enough equations to solve for all constants, which can happen with repeated factors. Let's try another example, this time with a more complicated denominator. Step 1. Factorize the denominator. This is a quadratic expression, and we need to find two linear factors. We can use the splitting the middle term method. We need two numbers that multiply to 6 times 3, which is 18, and add up to 7. Those numbers are 9 and 2. So we rewrite 7x as 9x minus 2x. Factoring by grouping gives us 3x plus 1 times 2x plus 3. Notice a small typo in the original document. It should be 3x plus 1, not 3x minus 1. Step 2. Split the fraction. Since we have two distinct linear factors in the denominator, the decomposition form is a over the first factor plus b over the second factor. Step 3. Clear the denominators by multiplying both sides by the denominator, 3x minus 1 times 2x plus 3. This simplifies to 8x minus 10 equals a times 2x plus 3 plus b times 3x minus 1. Step 4. Solve for the constants. Let's use the substitution method again. To find b, we substitute x equals 1/3, which makes the a term 0. We get 8 times 1/3 minus 10 equals a times 2 times 1/3 plus 3 plus b times 3 times 1/3 minus 1. This simplifies to negative 22 over 3 equals b times 0, which is 0 plus b times 2, 3 minus 1, or negative 1/3. Wait, let's reevaluate. 2, 3 plus 9, 3 is 11, 3. So we have 22 through 3 equals a 11 or 3. This means a is 2. Let's correct that from the original notes. Now let's find b. We substitute x equals negative 3 to 2, which makes the a term 0. This gives us 8 times negative 3, 2 minus 10 equals b times 3 times negative 3, 2 minus 1. Simplifying, we get negative 12 minus 10, which is negative 22, equals b times negative 9, 2 minus 1. This is negative 22 equals b times negative 11, 11, 2. Dividing both sides by negative 11th gives us b equals 4. Step 5. Substitute our corrected values a'2 and b4 back into the decomposition. The fraction becomes negative 2 over 3x minus 1 plus 4 over 2x plus 3. Step 6. Now we integrate these simple fractions. We use the formula from before. For the first term, we get 2 over the x coefficient 3 times the natural log of the absolute value of 3x minus 1. For the second term, we get 4 over the x coefficient 2 times the natural log of the absolute value of 2x plus 3. This simplifies to negative 2/3 natural log of 3x minus 1 plus 2 times the natural log of 2x plus 3 plus c. This is our final answer, verified using memo. Let's move on to an example that requires less work. Here, the denominator is already factorized for us. We can immediately jump to step 2, separating the fraction into its partial fractions. We have two distinct linear factors, x and x minus 1. So we write a over x plus b over x minus 1. This is the correct form for this decomposition. Step 3. Clear the denominators by multiplying by x times x minus 1. This gives us 3x minus 5 equals a times x minus 1 plus b times x. Step 4. Solve for the constants using substitution. First, let's substitute x equals 0. This makes the b term 0. We get negative 5 equals a times negative 1, so a is 5. Next, let's substitute x equals 1. This makes the a term 0. We get 3 times 1 minus 5 equals b times 1. This simplifies to negative 2 equals b. Step 5. Substitute our values a as 5 and b star 2 back into the partial fraction form. The expression is now 5 over x plus negative 2 over x minus 1. Step 6. Integrate. The integral becomes the integral of 5 over x minus the integral of 2 over x minus 1. This integrates to 5 times the natural log of x minus 2 times the natural log of x minus 1 plus c. A much simpler result thanks to partial fractions. This answer is correct. Now let's tackle our second type, repeated linear factors. We will determine the integral of 2x minus 2 over the quantity 2x plus 1 squared. The denominator is 2x plus 1, which is a repeated linear factor since it's squared. Step 2 is to set up the partial fraction form for repeated factors. Remember, we need a term for each power. So we have a over 2x plus 1 plus b over 2x plus 1 squared. Step 3. Clear the denominators. We multiply both sides by 2x plus 1 squared. On the left, it cancels. On the right, the first term becomes a times 2x plus 1, and the second term is just b. Step 4. Solve for the constants. The problem notes that there's only one value of x that will make a term 0. X equals negative 1/2. Substituting this gives us negative 1 minus 2 on the left and a times 0 plus b on the right. So b equals negative 3. But we have two constants to find, a and b, and we've only used one value of x. This is the exact situation where substitution isn't enough. A simple trick is to substitute another convenient value for x, like x equals 0. Substituting x equals 0 into our equation gives us negative 2 equals a times 1 plus b. We already know b is negative 3, so negative 2 equals a minus 3, which means a equals 1. Step 5. Substitute a equals 1 and b equals negative 3. The decomposition is 1 over 2x plus 1 minus 3 over 2x plus 1 squared. Step 6. Integrate. The integral of the first term is 1/2 times the natural log of 2x plus 1. The second term requires the power rule for integration. We rewrite it as negative 3 times 2x plus 1 to the negative 2. Integrating this gives us negative 3 times 1/2 times 2x plus 1 to the negative 1 all over negative 1. The negative signs cancel out. The final result is 1/2 natural log of 2x plus 1 plus 3 over 2 times 2x plus 1 plus c. Verified using memo. Let's explore an alternative and sometimes more direct way to solve the same problem without using two substitutions. Remember the method of equating coefficients? Let's apply it here. We expand the right side, 2x plus a plus b. We collect the x terms and the constant terms. Now we compare the coefficients of x on both sides. On the left, we have 2x. On the right, we have 2ax. Therefore, 2 equals 2a, which means a equals 1. Next, we compare the constant terms. On the left, we have negative 2. On the right, we have a plus b. So negative 2 equals a plus b. Since we just found that a is 1, we have negative 2 equals 1 plus b, which gives us b equals negative 3. Notice we found a1 and b3 very quickly and directly, which are the same values we found before. This method is often preferred when substitution alone isn't enough. Finally, let's explore an alternative way to perform the decomposition for the last example. This method works by manipulating the numerator. The goal is to make the numerator look like a part of the denominator, 2x plus 1. We want to force a 2x plus 1 into the numerator. We start with our fraction. In the numerator, we have 2x minus 2. We can rewrite negative 2 as plus 1 minus 3. This gives us 2x plus 1 minus 3. Now we substitute this back into our fraction. We have 2x plus 1 minus 3 over 2x plus 1 squared. Because this is a single denominator, we can split it. We can write this as 2x plus 1 over 2x plus 1 squared minus 3 over 2x plus 1 squared. The first term simplifies. 2x plus 1 cancels out, leaving 1 over 2x plus 1. So the decomposition is 1 over 2x plus 1 minus 3 over 2x plus 1 squared. As you can see, this is the exact same partial fraction decomposition we found using the other two methods. This technique of algebraic manipulation is a very elegant way to find the decomposition when the denominator is a repeated linear factor. Let's work through one more example involving repeated linear factors, this time with a power of 3. We have a repeated linear factor, x1 raised to the power of 3. Step 2. Split into partial fractions. We need a term for each power from 1 to 3, so we have a over x1 plus b over x1 squared plus c over x1 cubed. Step 3. Clear denominators by multiplying by x1 cubed. This gives us x squared plus 2 equals a times x1 squared, plus b times x1 plus c. Step 4. Solve for the constants. We only have one factor, x1, so x equal 1 is the only value that makes a term 0. Substituting x01, we get 1 squared plus 2 equals c. This simplifies to c equals 3. Great, we have our first constant. Now we need to find a and b. We'll need to use two more values of x. Let's pick easy ones like x at the 0 and xs 2. Substitute x in 0. We get 0 plus 2 equals a times 1 minus b plus c. So 2 equals a minus b plus c. Substitute x02. We get 2 squared plus 2 equals a times 1 plus b times 1 plus c. So 6 equals a plus b plus c. We now have two equations with a and b since we know c is 3. The first equation becomes a minus b equals -1. The second becomes a plus b equals 3. We can solve this system. Adding the two equations together, the b's cancel, giving us 2a equals 2, so a equals 1. Substituting a equals 1 back into a plus b equals 3 gives 1 plus b equals 3, so b equals 2. Step 5. Substitute our constants. a equal 1, b equal 2, c 3. The decomposition is 1 over x1 plus 2 over x1 squared plus 3 over x1 cubed. Step 6. Integrate. The integral of the first term is natural log of x1. For the other two terms, we use the power rule after rewriting them as negative powers. This gives us -2 over x1 minus 3 over 2 times x1 squared plus c, verified using memo. Let's look at another alternative method for solving this problem. This method is called substitution, but it's a bit different from our previous one. This works especially well when the entire denominator is a single repeated linear factor. The key idea is to perform a substitution u equals x minus 1. This makes the denominator much simpler. If u equals x minus 1, then x equals u plus 1 and dx equals du. Now we substitute everything into the integral. X squared plus 2 becomes u plus 1 squared plus 2, and x minus 1 cubed becomes u cubed. We have a new, simpler integral in terms of u. Next, we expand the numerator. U plus 1. Squared is u squared plus 2u plus 1. Adding 2 gives us u squared plus 2u plus 3. Since the denominator is a single term, u cubed, we can split the fraction into 3 simpler terms by dividing each term in the numerator by u cubed. This gives us u squared over u cubed, plus 2u over u cubed, plus 3 over u cubed. Simplifying these gives us 1 over u, plus 2 over u squared, plus 3 over u cubed. This is already our partial fraction decomposition, just in terms of u. The coefficients are already determined. Finally, we substitute back x minus 1 for u. This gives us our partial fractions. 1 over x minus 1 plus 2 over x minus 1 squared plus 3 over x minus 1 cubed. As you can see, this method provides the partial fractions directly without having to solve a system of equations. It's a very elegant and efficient technique when it applies. Let's quickly recap what we've learned today. We learned a powerful technique to integrate complex fractions by first separating them into simpler partial fractions. We first learned about proper and improper fractions and how to deal with the latter using long division. Then we focused on splitting proper fractions into partial fractions based on whether the denominator has distinct or repeated linear factors. We covered the two main methods for finding the unknown constants a, b, and c. The substitution method, which is quick but not always sufficient, and the method of equating coefficients, which is more robust. We also saw an alternative algebraic trick and a U substitution technique for certain cases. Finally, we applied this entire process step by step to several examples, turning difficult integrals into a sum of easy-to-solve natural logs, or power rule integrals. You are now equipped with a crucial tool for solving a much wider range of integration problems. The key is to practice and remember the correct form for each type of denominator. Thank you for watching this tutorial from Math Zone African Motives. If you found this helpful, please subscribe for more maths tutorials. Goodbye for now.